Choke coils reduce lamp filament buzz. Choke coils work by inductive reactance. They are inductors that oppose the flow of alternating current, or AC. When AC passes through a choke coil, the inductor creates a magnetic field that opposes the flow of current. This magnetic field reduces the amount of current that flows through the coil. As a result, choke coils can be used to reduce the noise produced by AC circuits. For example, they can be used to reduce the buzz from lamp filaments and reduce the hum from low voltage transformers. The key principle behind a choke coil's operation is inductive reactance, which is the opposition to the change of current flow in an AC circuit. Inductors, including choke coils, store energy in a magnetic field when current flows through them. This stored energy resists changes in the current. In an AC circuit, the current is constantly changing direction, which causes the inductor to repeatedly store and release energy. This process creates an opposition to the current flow, known as inductive reactance. The inductive reactance, denoted as X sub L, is proportional to the frequency, denoted as F, of the AC signal, and the inductance, denoted as L, of the coil, according to the formula X sub L equals 2 pi FL. This means that the higher the frequency or the inductance, the greater the inductive reactance. The higher the frequency or the inductance, the greater the opposition to the flow of AC. Choke coils are designed to have a specific inductance value that provides a significant inductive reactance at the frequencies of the noise that needs to be filtered out. For example, if a choke coil is used to reduce the hum from a transformer operating at 60 Hz, the coil would be designed to have a high inductive reactance at that frequency. When AC passes through the choke coil, the inductive reactance opposes the flow of current, which reduces the amplitude of the AC signal. This reduction in amplitude is particularly effective at the frequencies where the noise is most prominent. In the case of lamp filament buzz, the noise often originates from the rapid heating and cooling of the filament as the AC current changes direction. By reducing the amount of AC current that flows through the filament, the choke coil minimizes these temperature fluctuations and reduces the buzz. Similarly, in low voltage transformers, the hum is often caused by the vibration of the transformer cord due to the alternating magnetic field. By reducing the AC current that flows through the transformer, the choke coil minimizes the vibrations and reduces the hum. Choke coils are typically constructed by winding a coil of wire around a core material. The core material can be air, iron, or ferrite, depending on the desired inductance and frequency characteristics. The number of turns in the coil, the size and shape of the core, and the type of core material all affect the inductance of the coil. The inductance of a choke coil is measured in henries, denoted as H. A choke coil with a higher inductance will have a greater inductive reactance at a given frequency. Choke coils are used in a wide variety of applications to reduce noise in AC circuits. Firstly, they are used in lighting circuits to reduce lamp filament buzz. Secondly, they are used in power supplies to reduce transformer hum. Thirdly, they are used in audio circuits to reduce unwanted noise and interference. Fourthly, they are used in radio frequency circuits to filter out unwanted signals. When selecting a choke coil for a specific application, it is important to consider several factors. Firstly, the frequency of the noise that needs to be filtered out. Secondly, the inductance of the coil. Thirdly, the current rating of the coil. Fourthly, the physical size and mounting requirements of the coil. The frequency of the noise that needs to be filtered out will determine the required inductive reactance of the coil. The inductance of the coil should be chosen to provide a significant inductive reactance at the noise frequency. The current rating of the coil should be sufficient to handle the maximum current that will flow through the coil. The physical size and mounting requirements of the coil should be compatible with the available space in the circuit. In addition to reducing noise, choke coils can also be used to improve the efficiency of AC circuits. By reducing the amount of current that flows through the circuit, choke coils can reduce the power loss due to resistance. This is particularly important in high current circuits where the power loss can be significant. Choke coils are also used in power factor correction circuits. Power factor is a measure of how efficiently electrical power is used. A low power factor indicates that a significant portion of the electrical power is being wasted. Choke coils can be used to improve the power factor of AC circuits by reducing the reactive power. Reactive power is the portion of the electrical power that is not used to do work. By reducing the reactive power, choke coils can improve the power factor and reduce the amount of wasted energy. In summary, choke coils are inductors that oppose the flow of AC current. They work by creating a magnetic field that opposes the changing current, which reduces the amplitude of the AC signal. They are used in a wide variety of applications to reduce noise, improve efficiency, and correct power factor in AC circuits. The inductive reactance of a choke coil is determined by its inductance and the frequency of the AC signal. When selecting a choke coil, it is important to consider the frequency of the noise that needs to be filtered out, the inductance of the coil, the current rating of the coil, and the physical size and mounting requirements of the coil. Choke coils are a versatile and effective tool for improving the performance of AC circuits. They are widely used in electronic devices, power supplies, lighting systems, and other applications where noise reduction and efficiency are important. The principle of inductive reactance is fundamental to understanding how choke coils work. The ability of an inductor to oppose changes in current flow is what makes them so effective at filtering out unwanted noise and improving the performance of AC circuits. The design and construction of choke coils can vary depending on the specific application. Some choke coils are designed to operate at high frequencies, while others are designed to operate at low frequencies. Some choke coils are designed to handle high currents, while others are designed to handle low currents. The choice of core material, wire gauge, and number of turns in the coil will all affect the performance of the choke coil. Choke coils are often used in conjunction with capacitors to create filter circuits. A filter circuit is a circuit that is designed to pass certain frequencies while blocking others. Choke coils and capacitors can be combined to create low-pass filters, high-pass filters, band-pass filters, and band-stop filters. A low-pass filter allows low frequencies to pass through while blocking high frequencies. A high-pass filter allows high frequencies to pass through while blocking low frequencies. A band-pass filter allows a certain range of frequencies to pass through while blocking frequencies outside that range. A band-stop filter blocks a certain range of frequencies while allowing frequencies outside that range to pass through. The combination of choke coils and capacitors allows for the creation of highly effective filter circuits that can be used to remove unwanted noise and interference from AC signals. In addition to their use in noise reduction and filtering, choke coils are also used in impedance matching circuits. Impedance matching is the process of adjusting the impedance of a circuit to maximize the transfer of power. Choke coils can be used to transform impedance levels, which is useful in applications where the impedance of a source and a load are different. By using a choke coil to match the impedance of the source and the load, the maximum amount of power can be transferred from the source to the load. Choke coils are also used in resonant circuits. A resonant circuit is a circuit that oscillates at a specific frequency. Resonant circuits are used in a wide variety of applications, including radio transmitters, radio receivers, and oscillators. Choke coils and capacitors can be combined to create resonant circuits. The resonant frequency of a resonant circuit is determined by the inductance of the choke coil and the capacitance of the capacitor. By adjusting the inductance or the capacitance, the resonant frequency of the circuit can be tuned. Choke coils are an essential component in many electronic circuits. Their ability to oppose the flow of AC current makes them useful for a wide variety of applications, including noise reduction, filtering, impedance matching, and resonant circuits. The design and construction of choke coils can vary depending on the specific application, but the underlying principle of inductive reactance remains the same. The use of choke coils is a fundamental aspect of electrical engineering and electronics. A deep understanding of their properties and applications is essential for anyone working in these fields. The selection and application of a choke coil in a circuit requires careful consideration of the circuit's operating characteristics, the frequencies of the signals involved, and the desired outcome. The choke coil is not merely a passive component, it is an active participant in the circuit's behavior, influencing current flow, voltage levels, and signal characteristics. It's a fundamental building block for a wide variety of circuits and systems. When working with choke coils, it's important to consider their physical properties as well. Size, shape, and mounting style can all play a role in their performance and suitability for a given application. Additionally, the core material can influence the coil's behavior, especially at higher frequencies. Ferrite cores, for example, are often preferred for high-frequency applications due to their low losses. Understanding the nuances of choke coil design and application can greatly improve the performance and reliability of electronic circuits. They continue to be a vital component in modern electronics, from simple power supplies to complex communication systems. The more you learn about choke coils, the more you will appreciate their versatility and importance in the world of electronics.